Hello, chemistry. Good morning. I hope you guys had a wonderful weekend. Today we're going to talk about quantitative description of gases. So we're actually going to talk about a lot of equations today that you'll be using tomorrow, especially for your chapter review. So we're going to be talking about a lot of math. I'm going to be talking about a lot of what the equations actually mean. But stick with me. All right. So in 1662, Robert Boyle, he's pictured on the right there, discovered that pressure and volume of a gas are related to each other mathematically. This discovery and a lot of other scientists were working on stuff at the time, led to the gas laws. Gas laws are simple mathematical relationships between the volume, temperature, pressure, and quantity of a gas. Pressure and force. Before we get into equations, let's actually talk about how we measure these things. Pressure is defined as the force per unit area on a surface. So how much gas pressure is exerted on a surface. Newton is the SI unit for force, named after Isaac Newton, of course. Gas particles exert pressure on any surface with which they collide. More collisions equals more pressure. So if you have a higher temperature, you have more collisions, more pressure. If you have more molecules, you have more collisions, more pressure. And if you have a higher volume, so if you have more space, the more space you have, the less collisions, the lower the pressure. But if you condense that down, you now have more collisions, more pressure. Atmospheric pressure. The weight of the atmosphere is a result of the mixture of several gases, 78% nitrogen, 21% oxygen, and then 1% carbon dioxide, fluorine, chlorine, whatever else is up in the atmosphere, mostly carbon dioxide. The weight of the atmosphere at sea level is 10.1 newtons. So 10.1 newtons of force are exerted on something at sea level, whether it's a seashell, a human being, a can of soda, everything gets 1 atmosphere of pressure on top of it. We have a little bit less because we're a little bit higher up. There's not as much atmosphere above us versus at sea level, so we have a little bit lower atmospheric pressure. This is why water boils at lower temperatures the higher you go. Measuring pressure. Barometer. This is what we use to measure atmospheric pressure. I have one in my classroom right as you come in the door on the left, but I also have a picture of one over on the right hand side there. And these measure atmospheric pressure. The first person to use one was Evangelista Torricelli. In 1643 he invented the barometer, and he was using mercury and testing its behavior. He found out that mercury was exactly 1/114th, so it's 1/14 the density of water. So he expected, when he inverted a test tube like over on the right there with the mercury barometer, it to go up 1/14th the amount that water would. Water would go 14 times higher. He discovered that at 0 degrees Celsius, whenever mercury was sucked into a tube, it extended to exactly 76.0 centimeters or 760 millimeters. Units of pressure. We can use millimeters of mercury, which is how far mercury would travel up a column, up a column. So if you have lower pressure, it's going to go higher. Torr is 1 millimeter of mercury. It's named after Torricelli. Some people use it, some people use millimeters of mercury. They're basically the same thing. Atmospheric pressure. This is equal to average sea level pressure at 0 degrees Celsius. 1 atmosphere is equal to 760 torr, or 760 millimeters of mercury. For our system of pressure for SI, Blaise Pascal, he studied pressure in fluid systems. Remember that gases and liquids are both fluids because those molecules are allowed to slip past each other. 1 Pascal is the SI unit for pressure. It's the force exerted by 1 Newton acting on an area of 1 square meter. So 1 Pascal equals 1 Newton over meter squared. Remember, it's that surface to area collisions. Kilopascal equals 1,000 pascals, and 1 atmosphere So the pressure exerted by 760 millimeters of mercury is 1.01325 times 10 to the 5th pascals. I will usually give you that number. I won't require you to memorize that one. Standard temp and pressure. Because pressure and temperature affect volume, they affect everything about a gas, for a lot of experiments we keep pressure and temperature standard. Standard temperature and pressure is 1 atmospheric pressure and 0 degrees Celsius. Anything different and you move away from standard temperature and pressure. Boyles Law. This is a pressure for volume relationship. Doubling a gas's pressure reduces its volume by half, and tripling it reduces its volume to 1/3. So these are inversely proportioned. Boyles Law says the volume of a fixed mass of gas, so you know exactly how much is in there, varies inversely with the pressure at a constant temperature. And down below I have P1 V1 equals P2 V2. P is going to be the pressure of a gas and V is going to be the volume. P1 and V1 will be for your first gas. P2 and V2 will be after you've adjusted its pressure. So if you double it, then you're also going to double V2. A lot of these, what you're going to have to do is you're going to have to take your equation and get one variable, the one you don't know, alone. So if you knew P1 and V1 and you knew what the pressure was at V2, you could find out what the volume is. You could divide P1 and V1 by P2, and then you would get V2 all alone, and you would know what that new volume would be. Charles's law. This is a temperature and volume relationship. Jacques Charles in 1787, he found out that all gases expand and contract when heated in a very similar way. Oxygen behaves very similar to water vapor, which is very similar to bromine, which is very similar to argon gas. He found that raising a gas 1 degree Celsius increases its volume, this number 1 over 273 times. Inversely, cooling it 1 degree Celsius decreases its volume 1 over 273. So if you were to increase the volume of water vapor 10 times, you would increase its volume 10 over 273 times. Absolute zero. This is negative 273.15 degrees Celsius. This is 0 on the Kelvin scale. For Charles's law, we will be using temperature Kelvin. If you get a temperature Celsius, you need to convert it to temperature Kelvin. Temperature in Kelvin is directly proportional to a gas's volume, as you can see on the chart on the right. Increasing the temperature also increases the volume at a very set rate. So if you quadruple the temperature, you quadruple the volume. Here's the equation for Charles's law. The volume of a fixed mass of gas varies directly with the Kelvin temperature at constant pressure. So V1, volume 1 over temperature 1 is equal to volume 2 over temperature 2. So if you were looking for temperature 2, or excuse me, if you were looking for volume 2, like we were in the last one, what you would do is you divide V1 divided by T1, and then you times over the T2 and get that V2 all alone. A lot of it's just going to be algebraically moving these equations around, looking for the variable V1. If you want to find V1, you need to times T1 over to the other side. Gay-Lussac's law for pressure. This is a pressure-temperature relationship. The pressure of a fixed mass of gas varies directly with the Kelvin temperature at a constant volume. So, where the last one was looking at volume, now we're looking at pressure. And pressure and temperature behaves very similarly. If you increase the temperature, the pressure will also increase. These particles are moving faster. The combined gas law. This one is Boyles Law, Charles Law, and the Gay-Lussac Law all combined into one singular expression. As you can see on the left-hand figure here, we're taking all of these things and putting them together. It expresses the relationship between pressure, volume, and temperature of a gas when the amount is fixed. Next chapter, we're going to talk about what happens when the amount changes, but for this chapter, we're just talking about a certain amount of gas. So on this one, it's P1 over V1 divided P1 V1 divided by T1. So the pressure and volume over temperature 1 is equal to the the second pressure and the second volume over the second temperature. Dalton's Law of Partial Pressures. John Dalton, this is the English chemist who proposed atomic theory, also made up this law of partial pressures. He found that in a mixture of gases, the pressure is equal to all the pressures combined. So for the atmosphere, the pressure of nitrogen plus the pressure of oxygen plus the pressure of carbon dioxide and other gases equals 1 atmosphere. So a partial pressure, this is the pressure an individual gas mixture exerts. And Dalton's law of partial says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. So down on the right there you can see the total pressure is equal to gas A plus the pressure of gas B plus the pressure of gas C, so on and so forth. If you had 6, you'd have pressures D, E, and F. If you had 2, you'd have pressures A and pressures B. We can use Dalton's law of partial pressure for collecting gases by water displacement. So if we're boiling gases in a lab out of water, we can use this partial pressure to use the water vapor, and then what's left will be the pressure of our gas. So pressure of the atmosphere equals pressure gas plus pressure of H2O. So if you were going to find the pressure, if you knew the pressure of the atmosphere, which you should know is 760 torr or 1 atm, you can subtract the pressure of water vapor, and that will leave the pressure of gas alone. Just a little more algebra for you guys. So on 337, the review 1 through 5 and 10, 1 through 4 are all, well, number 2 you have to convert, and your conversions are on page 326. And then for number 5, use Boyles' law equation, and for number 10, use gases collected by water displacement equation on 336. Hope you guys have a wonderful Monday. If you have any questions about the review that's for tomorrow, feel free to email me. I will send you back what equation you need to use and whatever needs to be there. Might set it up so that I could do a couple and send them to you guys. We'll see. Let me know if you have questions and we'll go from there. All right, peace out.